Let's turn our attention now to section 5.6, and let's review indeterminate forms and talk about L'Hopital's rule. We've seen indeterminate forms of limits for as long as we've seen calculus. Going back to just the first sections of Cal 1, you start to see limits that look like this. We're going to take the limit as x approaches 0 of the sine of x over x. All right? And this result is difficult to come by. Eventually, we use a geometric argument that has to do with the area of a sector to find that this is equal to 1. But this is not a simple result to come by. And in fact, we generally have to go through that geometric argument because otherwise it's difficult to simplify this in any other way. But if we ask ourselves, why is this so complicated? Why is this so difficult? We note that, well, at the very beginning, if you just try to plug in that number 0, that's 0 over 0. And 0 over 0 is undefined because, well, division by 0 is undefined. We don't know what that means. So here, this is a complicated thing to try to resolve. That's what's called an indeterminate form. Whenever you have something that isn't a known value, if it's not a defined result, it's what's called indeterminate. Now, some forms that are undefined in a way that makes it apparent what the result is. So for example, if I say I want to take the limit as x approaches infinity of, let's say, in fact, let's use the same one, the sine of x over x. Here, that's also sort of strange, right? Again, you can't just plug in the numbers because it gives you something undefined, except in this case, you can use the squeeze theorem. After all, here you can say, well, the sine of x over x, that's bound between minus 1 over x and 1 over x. All right, sine of x is bound between minus 1 and 1. That's the range of the sine of x. And so sine of x over x is bound between minus 1 over x and 1 over x, which means that the limit as x approaches infinity of those is also related in this set of inequalities. But since we know what these results are, I know that as x approaches infinity of 1 over x, well, let's see, 1 over infinity is undefined. That's nonsense. Right, but we know that that means that you're not really plugging in infinity. That would be impossible. Infinity is not a number. What we're saying is we're letting x become infinitely large. We're letting x get bigger and bigger. And as x gets bigger and bigger, 1 over x gets smaller and smaller, until eventually you get to 0. Likewise, it would be impossible to say negative 1 over infinity. Infinity is not a number. You can't divide by infinity. That's nonsense. But that's not really saying plug in infinity. It's saying I want numbers that are getting bigger and bigger. If I take negative 1 over very big numbers, I get numbers that are closer and closer to 0. Right? They're negative numbers, but they're getting closer and closer to 0. So here, both of these limits are 0. And so by the squeeze theorem that we see in Calculus 1, this result must also be 0. So note that just because an expression is undefined, so for example 1 over infinity, that doesn't mean that it's not something we can immediately resolve. Some things are undefined in a way that is predictable. Yeah, that doesn't mean anything directly, but the only way I can get something like that is because something like this is happening. That's not what we're talking about here. Here we're talking about ones where it really is not resolvable. It's not really something you can easily tell what's supposed to happen. These are called indeterminate forms, and the two indeterminate forms that we're going to most focus on are going to be 0 over 0 and infinity over infinity. Whenever you have something like 0 over 0, that's not automatically going to give you a result. Sometimes 0 over 0 will be 1. Sometimes 0 over 0 will be 5. Other times 0 over 0 will be 0. And other times 0 over 0 will be undefined. It'll depend entirely on the problem itself. Same thing for infinity over infinity. It doesn't necessarily mean any one thing. This is indeterminate, meaning we cannot determine a priori what these are equal to. We're going to have a few other indeterminate forms. We're going to have negative infinity over infinity is also indeterminate. Negative infinity over negative infinity is also indeterminate. And infinity over negative infinity is also indeterminate. And you say, okay, yeah, but that's just changing the positive and the negative. Well, that's true, but we are going to have a few other indeterminate forms that don't look anything like these. For example, 1 to the infinity. And 1 raised to any power should stay 1. 1 to the first, 1 to the second, 1 to the third, 1 to the fourth. It's always 1. But if something is infinitely big, doesn't that mean that should make that be infinite? Well, maybe. Maybe not. We don't know. We're indeterminate. We can't determine ahead of time what that means. Something like infinity to the 0. If that's already infinite, well, then it should stay infinite. Well, yeah, but anything to the 0 power is equal to 1. So which is it? All right? What about infinity times 0? Anything times 0 must be 0. Oh yeah, but infinity times anything must be infinite. So which one wins? Which one's stronger? Yeah? So these are examples of what we mean by indeterminate forms. We're going to focus mostly on these. These, it's going to turn out that we're not going to handle them separately. We're going to rewrite these using algebra and trigonometry until we can turn these into these. So that's why we focus on these primarily, because everything's either going to start like one of these or we can change it into one of these. All right, so let's talk about these two and how we're going to evaluate limits like this. This is one example, by the way. Notice if I try to substitute in 0, I get 0 over 0. That's indeterminate. That's why I can't just say, oh, that's equal to something. This takes a decent amount of effort to find. It's a geometric argument that we see all the way back in Cal 1. What we're going to see now is a way of doing that without the geometric argument. In fact, not just this one, but any problem that has that form of 0 over 0 or infinity over infinity. So here, let's see a theorem that we see a version of in Cal 1. We see the mean value theorem. Here we're going to be looking at a more advanced version of that called the extended mean value theorem. All right, extended mean value theorem. We're going to start off with two functions. We'll call them f and g. And we're going to define them on a closed interval from a to b. So let f and g be functions that are continuous on a closed interval, and we'll call that interval from a to b, and differentiable on the open interval. So it may not be differentiable at the endpoints, but everywhere in between. Differentiable on the open interval from a to b. Okay. Now, we want that the function g, if you take its derivative, it's not going to equal to 0 anywhere in the open interval. Okay, so we know g is differentiable, which means we can find its derivative. But once we find its derivative on this interval from a to b, it should never be 0. Assuming all these things are true, there exists a value c that's in the interval from a to b, somewhere in the open interval from a to b, not a or b, such that f prime at c divided by g prime at c is equal to f at b minus f at a divided by g at b minus g at a. Just like that. Okay. Let's remind ourselves of just what the regular mean value theorem said. Here I'm not going to write out the theorem. Let's just go ahead and give a quick illustration. Recall, the regular mean value theorem said this. Let's say you have a function that is continuous on the interval from a to b and differentiable on the open interval from a to b. So continuous between here and here, including the endpoints, and differentiable between here and here, not necessarily including the endpoints. All right, so you have a function. And we'll just draw it like that. Okay. Now, create a secant line between the two endpoints. Create a line that passes through, a straight line that passes through the beginning and the endpoint here. All right. So here, we're going to take the slope of this line. If this is A, then this must be f at A. If this is B, this must be f at B. That's how functions work, yeah? You know the x value, plug it into the function, that gives you the y value. So the slope of this line is going to be the difference in the y value, so f at b minus f at a. Now you start to see how that looks familiar. F at b minus f at a over b minus a. Change the y values over the change in the x values. What the mean value theorem says, not the intermediate value, what the mean value theorem says is that, okay, once you find the slope of that, I guarantee you that somewhere between these two endpoints, it doesn't tell you where exactly, it just tells you it's there somewhere between the endpoints of that curve, you're going to find a point where the derivative at that point, the slope of the tangent line, is equal to the slope of this secant line. So the extended mean value theorem does something similar, except it does it with two functions like this. Because it's doing it with two functions like this, it's something that's difficult to draw. So instead, we're going to prove it algebraically, or analytically, I guess I should say. So the proof of the extended mean value theorem, we're going to say, let's begin with a function that we're going to define based off of the two functions f and g. All right, so we'll call it h. We'll say let h of x be equal to f at x minus f at b minus f at a over g at b minus g at a times g at x. Okay? So here we're taking the two functions, f and g, and we're saying take f of x, subtract away this number, and note these a and b's are constants, so this whole thing is a constant, even though it's a big, funny-looking constant. F at x minus a constant times g of x, and that's going to equal to h of x. All right? H of x isn't something that we've computed, it's just that's how we're defining it. We're saying, okay, if you put f and g together this way, we're going to call it h of x. Okay, well, why would we want to put those two together in just that way and call it a new function? Well, look what happens if I plug in the endpoints into this new function. Let's say I want to find h at a. Well, the way functions work, that means that x is being replaced by the value a, which means so are those. So that's going to be f at a minus f at b minus f at a over g at b minus g at a times g at a. Again, these x's are being replaced by a's. Okay. I could then combine these two expressions together by just giving them a common denominator. Okay, so I could write this as f at a times, let me put that in brackets, g at b minus g at a over, and again, I'm just going to give them the common denominator, g at b minus g at a. Okay. Those two would cancel out, so technically nothing's changed. And then over here, I'm going to say minus f at b minus f at a, and again over g at b minus g at a And that whole thing is being multiplied by g at a. Okay? And now I can even combine these. Since they have a common denominator, I can distribute some stuff here and then combine everything together. So that'll be f at a times g at b minus f at a times g at a. All right, now that's minus g at a times f at b. So minus, let me distribute this one out. So that's going to be f at b, g at a. And then minus a minus, so that becomes a plus, f at a times g at a. Over that common denominator, g at b minus g at a. Just like that. And now you notice a couple of things subtract away, literally a couple, that one minus that one. So those are gone. So now we can write this as f at a times g at b minus f at b times g at a over g at b minus g at a. Like that. Now you look at that and you say, well, that doesn't look particularly special. I'm not seeing why that is the result that I wanted. Well, you wouldn't, at least not on its own. But look what happens when I plug in the other endpoint. Here I plugged in A. What if I plug in B here? What if I plug in the other value in my interval? Well, let's see. If I plug in H at B, that's going to be F at B minus F at B minus F at A over G at B minus G at A times G at B. And again, same thing, except now instead of A's, I'm plugging in B's for both of those. All right, so we can go ahead and expand those. Give them a common denominator. That's F at B times G at B minus G at A over G at B minus G at A minus this stuff over here. So G at B times F at B minus F at A. And now they have a common denominator, which means in the next step I can combine them. So minus G at A, like this. Okay? But now, of course, I can distribute. So that'll give me F at B times G at B minus F at B, G at A. Okay? Minus G at B, F at B. I'm going to flip those around and put the F first. F at B times G at B. And then double negative makes that a plus. So it'll be F at A, G at B. And that's all over a common denominator, G at B minus G at A. And now let's see, two of these should subtract away, right here and here. F at B, G at B minus F at B, G at B. And we're just left with these. I'm going to go ahead and put the positive one first. So that's equal to F at A, G at B minus F at B, G at A over our common denominator, G at B minus G at A. And now, note that these are identical. F at A, G at B minus F at B, G at A over G at B minus G at A. These are identical. So that means that H at A is equal to H at B. So now we're going to invoke a theorem from Calculus 1, which was Raleigh's theorem, or Rolle's theorem, depending on where in the world you're from. Some people pronounce it differently. So let's see here. Recall either Raleigh's or Rolle's theorem, which states that if you have a function that is continuous on a closed interval, so here let's write it this way. Let in fact, let me call it H just to keep it the same as this one. Let H be a function that is continuous on a closed interval from a to b and differentiable on an open interval from a to b, so everywhere except maybe at the endpoints, right? Such that h at a is equal to h at b, then there exists a value c in the interval from a to b, and it can't be either endpoint, it's in the open interval, such that h prime at c is equal to 0. Or in other words, you give me a function that's continuous on a closed interval and differentiable on the open interval, and the endpoints have the same height at h at a and h at b are both at the same height, like that. Then there exists some points somewhere in between these two, so that if I take the derivative of the function at that point, the derivative is going to be 0. In other words, the tangent line is horizontal. But that's what we have here. After all, h is the difference of two functions, which means it's a function. Okay? The two functions that it's made out of are continuous on a closed interval from a to b and differentiable on an open interval from a to b. So h will also have those properties. So h is a function continuous on the closed interval from a to b and differentiable on the open interval from a to b, such that, and here we've proven that h at a is equal to h at b. So that means there must exist some number c in that interval so that h prime of c is equal to 0. So there exists some value c in the interval from a to b such that h prime at c is equal to 0. Well, yeah, but we know what h is. H is f at x minus f at b minus f at a over g at b minus g at a times g at x. So we're saying if this right here is equal to h of x, then if I want to find h prime of x, well, then I should take the derivative of this thing. All right? So if this is equal to h of x, if I want to find h prime, that's the derivative of this part right here. But these are just differentiable functions. I know how to take the derivative. So that means that h prime of x is equal to, well, this is just the difference of functions, and since derivatives are linear operations, I can take the derivative of the first part minus, separately, the derivative of the second part. All right, well, if f is differentiable, then its derivative exists. We can call it f prime. Minus, now remember, this is just a constant. Yeah, it's a constant found using f and g, but it's still just a number. So the derivative of a number times g, because of linearity, we don't worry about the number, and we just take the derivative of g. All right? So here that's going to be that same function, f at b, that same function, that same number, minus f at a over g at b minus g at a times the derivative of g. Like that. So, given what we just found up here, there exists a value c such that this is equal to 0 if I plug in c. So there exists a number c in the interval from a to b such that, okay, I found the derivative. Here's h prime, but I want to plug in x is equal to c. Okay, so then that would give me f prime at c minus f at b minus f at a over g at b minus g at a times g prime of c. I'm just taking these and substituting in c, and that's going to equal to 0. All right, h prime of c is equal to 0. So now we're almost done. Here, let me add this to both sides of the equation. If that's h prime of c is equal to, if I add this to both sides, well, positive and a negative are going to subtract away. That's going to be 0. And here, 0 plus that is just going to give me that. So moving that over, that's going to give me f at b minus f at a over g at b minus g at a times g prime of c. But now I can divide both sides by g prime at c, and that gets me my result. F prime of c over g prime of c is equal to f at b minus f at a over g at b minus g at a. And that is the result we were after. After all, what we were looking for was to show that this one, that given two functions f and g that are continuous on the closed interval a to b and differentiable on the open interval a to b, and such that g prime of x was not equal to 0 for x in that interval, there exists a value c. There exists a value c such that f prime at c over g prime at c, is equal to f at b minus f at a over g at b minus g at a. So this concludes our proof. So now, using the results of this proof, we can now prove what's called L'Hopital's theorem, or also sometimes called L'Hopital's rule, which is a very useful way of evaluating certain indeterminate forms. Theorem. And I believe this textbook calls it L'Hopital's rule, so I'll go ahead and follow suit. L'Hopital's rule. Okay. We're dealing with two functions that are differentiable, in fact, same conditions that we had over here. Let f and g be functions that are differentiable on the open interval from a to b, containing a value c except possibly at c. So here you have two functions that are differentiable everywhere in here except maybe at one number. Right? If your function is differentiable on the interval from 0 to 100, it's differentiable everywhere in there except maybe at the number 5. There's a single point where maybe it's not differentiable. Maybe it is, but again, we have the possibility that it's not. So now let's assume that g prime of x is not equal to 0 anywhere in the interval except, again, maybe at c. If the limit as x approaches c of f of x over g of x is indeterminate, I don't know how to spell, indeterminate, there we go, of the form 0 over 0, infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over negative infinity, any of those combinations. If this limit is any of those indeterminate forms, then the limit as x approaches c. That should be the c right there, that same c that we had up in the conditions of the problem. The limit as x approaches c of f of x over g of x is equal to f prime of x over g prime of x. Note the conditions on this rule, on this theorem, require that your function's quotient have a limit that's of one of these 5 forms. If it doesn't look like one of these 5 forms, it is not valid to use L'Hopital's rule. In some of our examples that we'll see in this lecture, as well as some of the examples in the homework problems, you'll note that in some of the problems, you'll have some other indeterminate form, something that might look like infinity over 0 or something of that nature, in which case L'Hopital's rule is not valid. What do you mean it's not valid? I mean you'll get the wrong answer. So it has to be one of these 5 forms, or something that can be rewritten into one of these 5 forms. So let's take a stab at proving L'Hopital's rule. Thankfully, since we now have the extended mean value theorem, the proof of L'Hopital's rule is imminently accessible. So let's begin with, let's take our functions. Now, in fact, let me go back to the previous page here. You'll note that f and g are differentiable on an interval except possibly at c, which means we may have an issue at c. The value might be either undefined, or it might have a limit that's different from where you expect it to be. Remember, that's what it means for a function to not be differentiable at a point. You might have a function that looks like this, where you're going from here's a and here's b over here, and you might have it do something like this, where the point is completely missing, and here would be our c. Or you might have something where it's here's your a, here's your b, here's your c, and it's not missing, but it's just somewhere else. It's somewhere where it's not expected to be. The point is jumped off somewhere. It's a discontinuous function. Or you could have something that's completely disconnected, where your a is up here and your b is down here, except of course that won't happen in this case because, again, our limit as you approach x equals to c is going to be 0 for both f and g. So that means that the limit from the left and the limit from the right of f must both be the same. And in fact, they both must approach 0. Same thing for the limit from the left and the limit from the right of g. They must be the same, and they must both be approaching 0. So here, you can't have a situation where it's approaching something from one side and something else from another side. That wouldn't happen, because otherwise our limit would not equal to 0. It wouldn't equal to anything. So here, this one won't happen, but it could still be either of these two. Okay, so note that we do know that this limit should equal to 0. So, when your x value is approaching c, your y value is approaching 0. So what we want to do is we want to plug in that hole. We want to say, okay, if there was no point there, let me fill a point in there. Or if the point was somewhere else, let me bring it down so that it's right here. So the way we're going to do that is we're going to define 2 new functions. Note that our function f is continuous and defined everywhere except maybe at that point. Okay, so that original f is perfectly fine everywhere except that point. So what we're going to do is we're going to define a new function. We're going to call it capital F. And it's going to be the same as little f most of the time. In fact, everywhere except at c. So if x is not equal to c, if you're not there, you're perfectly happy using the old function. But if your x is equal to c, well then there might not even be a point there. Or there might be a point, but it might be somewhere else. We want it to be there. Well, what is there? Well, if the limits are both 0, then the point must be at c comma 0. Okay, so that's going to be 0 there in the case that x is equal to c. And since g has the same setup, the same possibility of being either undefined or defined differently at c, we're going to define capital G in the same way. We're going to take it to equal to little g, so long as x is not equal to c, or we're going to have to equal to 0 when x is equal to c. All right, so we're going to do with both of those functions. All right, so now note that f and g are differentiable on the interval from 0, not 0, I guess it should be c. So f and g, the new functions, are differentiable on the interval from little c up to x. Right? Just because we define the point there doesn't mean it's necessarily differentiable now, right? It's continuous at that point, but we've seen plenty of examples in Cal 1 where, yeah, that function's continuous, but it's still not differentiable there. Okay? So the function is continuous at that point now. That's good, but it still may not be differentiable. Okay, well, we have what we have. These new functions are differentiable on the interval starting after c, just like little f was. Just like little f was. And because we have filled in the hole now, well, again, it may not be differentiable, but it is continuous. Or rather, they are continuous. So f and g are differentiable on the interval from c up to x. Again, that may not include the c. And they are continuous on the interval from c up to x. And now you do include your c, because again, you filled in the hole. Where x is any number between c and b. So here you said, okay, pick some value out here, not at the endpoint, but somewhere in between this point that was under contest and this endpoint here. So let's call it x, right? And it could be anywhere along the lines, it doesn't really matter. Because here, we don't really care about points far away from c. The proof is going to go toward c. We're going to have our x values approach c, because after all, that's what we're trying to prove. We're trying to prove what happens when x approaches c. So here, we're okay with it being somewhere around c, and it doesn't matter how far, just somewhere nearby, so that we can take this and have it approach c. So now, we can use the previous theorem. By the extended mean value theorem, we get that there exists some value, which we're going to call z, yz, because we're already using x for other stuff. There exists a value z in the interval from c up to x, right, in the open interval here between the endpoints where the function is continuous and differentiable. Here. There exists a z somewhere in the interval such that capital F prime at z over capital G prime at z is equal to f at x minus f at c over g at x minus g at c. By the extended mean value theorem, there exists some point in between here such that f prime at that point in between over g prime at that point in between is equal to f at the endpoint minus f at the beginning point over g at the endpoint minus g at the beginning point. And that's what we proved in the extended mean value theorem. Now notice that when x is equal to c, f is equal to 0. A little simpler way of saying that is f of c is 0. So here, by definition, both of these are 0. By definition, wow, that was really bad. That was really badly misspelled, wasn't it? By definition, these equal 0. Right? Up here. Whenever your x is equal to c, your g at x is 0. Or in other words, g at c is 0. Likewise, f at c is 0. So both of those are 0. Which means I can just write that as f of x over g of x. I don't need those because they're both 0. Oh yeah, but as long as x is not equal to c, which it's not, right? Here x is a number that's different from c. So long as x is not equal to c, capital F is the same as little f, and capital G is the same as little g, right? We know c and x are different. Okay, so c is not equal to x. So here, capital G and little g are the same. And same thing up here. As long as x and y are not the same, capital F and little f are the same. Just like that. Now, one thing to notice over here is we can kind of say the same thing. Capital F prime z. Well, again, z is some number between c and x. So among other things, c is not equal to z. Here, note, c is not equal to z, right? Z is somewhere in between them, which means it can't be either one. Okay, so if z is not equal to c, that means that capital F and little f are the same. So here, f at z, capital F at z, is the same as little f at z. Oh, but I want a derivative. Okay, well then it's going to be the derivative of little f at z. So here we can write this side as being f prime of z using the little f. And same thing for this one. Since I know c is not the same as z, well then g at z is the same as little g at z, because z is not equal to c. Oh, but if I want the derivative of capital G at z, that's got to be the same as the derivative of little g at z. So here I can write that as little g at z, like that. So now, notice as x approaches c from the right. Now here I'm doing everything from the right-hand side. Incidentally, this proof only shows what's happening on this side of the point. The exact same thing could be said for the left side. So here, if you just switch these around so that x was on the other side of c, that'll give you the other side of the proof. So here I'm really only proving half of it, but the other half is identical except these are backwards. Here, that's why I'm saying from the right, because here I'm only handling the right-hand side of the illustration. Notice that as x approaches c from the right, well, z is stuck somewhere between c and x, which means z is over here to the left of x. So if this x is approaching c, z is still stuck in between. So that means that z will also be forced to get closer to x, to c. If x is approaching c, then z is being squeezed in between them. So z has no choice but to also approach c. Notice as x approaches c from the right, we get that z approaches c from the right. Right? Z approaches c from the right. Z is stuck in between. So if this one is getting closer and closer, if it's moving toward the left, towards c, then z has no choice but to do the same. Since that's true, yeah? So the limit as x approaches c from the right of little f of x over little g of x. That's going to be the same as the limit as x approaches c from the right of f prime of z over g prime of z. And again, all I'm doing is I'm saying, hey, look, that one there is equal to that one there. So the limit of that one will equal to the limit of that one. Okay? But now, notice that that means that as x approaches c, that's the same as saying z approaches c. So that's going to be the limit as z approaches c from the right of f prime of z over g prime of z. Just like that. So these remain the same, but now I'm replacing this limit with this limit since they are equivalent. But now, notice that I have, that's the limit as z approaches c of f prime of z over g prime of z. These are all exactly the same, so I could just substitute. Because after all, z is just some number. Doesn't matter what we call it. So here, we can write this as the limit as, and here let's use a more traditional symbol, limit as x approaches c from the right of f prime of x over g prime of x. And there we go. So now this shows that the limit as x approaches c of f of x over g of x is the same as the limit as approaches c from the right of f prime of x over g prime of x. The same proof can be applied to show the other side, namely that the limit as x approaches c from the left of f of x over g of x is the same as the limit as x approaches c from the left of f prime of x over g prime of x. But if the limit from the left is the same as the limit from the right for both, then that means putting those together means that the limit as x approaches c from the left and right, well, that's just the traditional limit. The limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. Notice this shows you that it's true as long as the limit of the numerator and the limit of the denominator both approach 0. We had other indeterminate forms listed in the theorem as well, namely infinity over infinity and namely infinity over infinity. Note that if f of x over g of x, if the limit as x approaches c of f of x over g of x is of the indeterminate form infinity over infinity, we can write the limit as x approaches c of 1 over f of x over 1, I should have those backwards. 1 over g of x divided by 1 over f of x. Right? Notice these do mean exactly the same thing. Even without a limit, 1 over g of x divided by 1 over f of x is the same as f of x over g of x once I reciprocate. So if those are equal, their limits are equal. But now notice, if g of x is approaching infinity, 1 over g of x must be approaching 0. And likewise, this one approaches 0 as well. If f is approaching infinity, 1 over f must be approaching 0. And so this applies as well to infinity over infinity. Right? So L'Hopital's rule applies in this case as well. Applies to cases of infinity over infinity. And that concludes our proof. Right? We show that if you have a function, a pair of functions that are differentiable on an interval from a to b, except maybe at some value c, assuming that the denominator's derivative is not 0, then if the limit as x approaches c of f of x over g of x is of one of these indeterminate forms, then the limit as x approaches c of f of x over g of x is equal to, and you know what, I said it and I never actually wrote it, it's equal to the limit as x approaches c of f prime of x over g prime of x. The way I stated the theorem before is not correct, is it? These aren't equal to each other. Their limits are equal to each other. Huh? Okay. So let's take a look at some examples of using this, and also let's take a look at an example where you shouldn't use this. Remember, this is only for these forms. So let's take a look at an example where you can absolutely use this. In fact, it's the one that we worked very hard in Cal 1. Let's find the limit as x approaches 0 of the sine of x over x. Okay. Notice that if I try to just plug in x equals to 0, I'm going to get, sine of 0 over 0, right? Which is, of course, invalid. That doesn't mean anything. Note, if I substitute 0, I get sine of 0 over 0, and I know the sine of 0 is 0 over 0. Okay, so right there, that's a non-answer. If you tell me my limit is 0 over 0, I'm going to say, yeah, well, that's nice, but that doesn't mean anything. What's your limit? Oh, it's something that I just made up that doesn't make any sense. Okay, well, that's what that is. But because it's this particular non-determinate form, indeterminate form, we can say, okay, I may not know what this is equal to. 0 over 0 doesn't make any sense. But by L'Hopital's rule, because it comes out to be 0 over 0, if I try to substitute, I can now write this is equal to the limit as x approaches 0. Notice that doesn't change. Of the derivative of the numerator, d dx of the sine of x, over the derivative of the denominator, d dx of x. Notice I'm not using the quotient rule. I'm not saying the derivative of the whole thing. I'm saying the derivative of the top, separately the derivative of the bottom. That's one mistake people will make. They'll try to use the quotient rule to take the derivative of this. Not the quotient rule. It's the derivative of the top, separately the derivative of the bottom. This is going to equal to the limit as x approaches 0. The derivative of the sine of x is the cosine of x. And the derivative of x is equal to 1. All right, the derivative with respect to x of x is equal to 1. Notice that I don't need to write the 1 there anymore. That's just the limit as x approaches infinity of the cosine of x. Limit as x approaches 0 of the cosine of x. That shouldn't change, right? Oh, but I know how to do that. That's not indeterminate. I can just plug in 0. What's the cosine of 0? That's equal to 1. So here, this limit is equal to that limit. But I just found that that limit is equal to 1. Okay, so that means my original limit must also equal to 1. The limit as x approaches 0 of the sine of x over x is equal to 1, which is nice. Note that you're sometimes going to have to chain use of the theorem, meaning you're going to have to use the theorem iteratively. One, then again, then a second, then a third, then a fourth, and so forth. So for example, let's say we want the limit as x approaches infinity of e to the power 2x over x squared. Okay? Once again, if I tried to substitute in infinity, that would give me a nonsense answer. It would give me, e to the infinity over infinity. It would give me something infinitely big over something infinitely big. That's nonsense. If you write infinity over infinity, that's not even wrong. Right? It's a non-answer. I had a professor once upon a time who liked to say things were wrong, but you could be worse than wrong. You could be not even wrong. The example he used to give was, if I ask you what's 2 plus 2 and you say 5, that's wrong. If I ask you what's 2 plus 2 and you say potatoes, that's not even wrong. That's not even in the same category of an answer. Right? It's a random noise that one made. So saying this is equal to 7 is wrong. Saying this is equal to infinity over infinity, that's not even wrong. It's not even good enough to be classified as wrong. Okay, but by L'Hopital's rule, we know that if this is of that unusual infinity over infinity form, we can write this as the limit as x approaches infinity, so that's going to stay the same, of the derivative of the top over the derivative of the bottom. All right, we can do that. The derivative of e to the 2x is e to the 2x again. Let me not forget my limit here, otherwise I'll have to squeeze it in, and that won't look nice. So it'll be the derivative of e to the power is, again, e to that power. Oh, but now by the chain rule, I have to multiply by the derivative of that power, which is just the number 2. Okay. Over, now I want the derivative of the denominator. The derivative of x squared is just 2x. I notice these two divide away. 2 divided by 2 is equal to 1. And I'm left with this is equal to the limit as x approaches infinity of e to the 2x over x. And notice that that is also indeterminate. If I say, okay, x approaches infinity, that's going to be infinitely big, and that's going to be infinitely big. So this is also of an indeterminate form. Oh, but that means L'Hopital's rule applies to this one as well. So, by L'Hopital's rule, we can say this. Here, whenever I use L'Hopital's rule, let me put the following symbol, L''H. That's something I got used to doing years and years and years ago, because it Later on, when you're going through your notes, you want to say, well, how did I do that? Oh, LH, L'Hopital's rule. L'Hopital's rule is not the single most important thing in limits, in calculus, or anything of that nature, but it is something that's useful enough that it shows up from time to time. So here, I've made a habit of writing LH to remind myself, oh yeah, that's where that came from. Because there are other techniques for evaluating limits, and we don't want to have to go through all of them every time I read my own writing. So here I'm going to do the same thing. I'm going to use L'Hopital's rule. By L'Hopital's rule, that's going to be the limit as x approaches infinity of the derivative with respect to x of the numerator over the derivative with respect to x of the denominator, which is the limit as x approaches infinity of, well, again, I already know what that derivative is. It's 2e to the 2x. But my denominator, the derivative of x with respect to x, that's just the number 1. So here, that's equal to the limit as x approaches infinity of, and here I don't need to write the number 1. I can just write 2e to the 2x. Oh, but that's not indeterminate. I know what that's equal to, right? Here, that limit is undefined, it's undefined. It goes to infinity. So here, as x approaches infinity, e to the 2x, that's also going to approach infinity. And times 2, well, that doesn't change anything. It approaches infinity. So here, we could say this is undefined, right? The limit, it just does not exist. But it does not exist in a very particular way. It goes off to infinity. So in Cal 1, you learned that a shorthand way of writing that, instead of writing out this limit does not exist but tends toward infinity, usually you just write goes to infinity. Or some people even write equals infinity, which I prefer not to do, but it's acceptable as well. That's also a common notation. So there we go. So this is equal to this is equal to this. But this one goes to infinity. Oh, so that must mean that the one I wanted also goes to infinity. Limit as x approaches infinity of e to the 2x over x squared goes to infinity. Or equals to infinity if you're inclined to use that notation. Right? Note that infinity over infinity is nonsense. It will sometimes give you something that goes to infinity. Other times, infinity over infinity will be like the number 12 or something of that nature. So here, give this a try. You're going to be using L'Hopital's rule. Obviously, that's all we've done in this section. See if you can get through taking the limit as x approaches 0 of the sine of 5x divided by the tangent of 9x. Okay? Go ahead and give that a try. Pause the video if you need to get the extra time. And whenever you have the result, go ahead and unpause the video and we will go through it together. Okay, so let's take a look. We're going to take the limit as x approaches 0. Notice if I just try to plug in 0, that's going to be sine of 0, which is 0, over tangent of 0, which is also 0. So just like that first example, 0 over 0, well, that's indeterminate. That's, the answer 0 over 0 is, it's not even wrong, right? So here we can use L'Hopital's rule. That's going to equal to the limit as x approaches 0, and we're going to be taking the derivative of the top separately from the bottom. All right, the derivative of the sine of something is the cosine of that something. But now the chain rule tells me to take the derivative of that inside and multiply it here. Denominator, same thing, derivative of tangent. Well, that's secant squared. But now by the chain rule, I need to multiply by the derivative of that argument, which is 9. Okay. Now we want to check. Let's try to plug in 0 now. If we still get something indeterminate, we're going to use L'Hopital's rule again. But if not, that's it. We're done. You only use L'Hopital's rule in the case of an indeterminate form. All right? So here we're going to say, okay, let's see what happens. If I substitute in 0, cosine of 0 is 1. So 5 times 1 is 5. That will not be indeterminate. It doesn't matter what the denominator is. Indeterminate forms for using L'Hopital's rule are either 0 over 0, infinity over infinity, negative infinity over infinity, something of that nature. So if this is 0, infinity, or negative infinity, then we may be able to continue. But this is the number 5. So it doesn't matter what the denominator is. We're done using L'Hopital's rule. We may not be done with the problem, but we're done using L'Hopital's rule. So here that's going to be cosine of 0, that's 1, and times 5 is going to equal to 5. Okay, 9 times 0 is 0. The secant of 0 is 1, and if I square that, that's still 1. But if I then multiply that by 9, that's going to give me my result. So here, this limit is indeterminate, but this limit is just 5 over 9. And so by L'Hopital's rule, these two are equal to each other. So the limit as x approaches 0 of the sine of 5x over the tangent of 9x is equal to 5/9. Just like that. Okay. Let's take a look at a couple more examples. The next one is a little bit different because, yes, you can use L'Hopital's rule, but, well, no, you can't use L'Hopital's rule. So I'm going to ask you to give this a try. This is not exactly a trick question because, yeah, you can use L'Hopital's rule. The problem is that when you use L'Hopital's rule, something, well, it's kind of annoying happens. So I'm going to ask you to give this a try. Go ahead and pause the video and go through this problem and see if you can evaluate the limit. You will probably start by using L'Hopital's rule, and then in a moment you'll get annoyed with that, and even when you get annoyed with that, you might need to find something else to use. So go ahead and give this a try. I'm not going to ruin the surprise exactly just yet by telling you how to do it. Pause the video, and when you get an answer or when you get thoroughly frustrated with it, go ahead and unpause and we'll go through it together. Alright, so if you did it by L'Hopital's rule, you notice something unusual, namely that you never finish. Because look what happens if you use L'Hopital's rule once like this. That's going to be the limit as x approaches infinity of the derivative of the top. Okay, well that's easy, right? Incidentally, that's infinitely big and that's infinitely big. So infinity over infinity. That's definitely something you can use L'Hopital's rule on. Okay, so let's use L'Hopital's rule. The derivative of x is just 1. Okay, so that makes things easy. Now my denominator. Okay, so let me go ahead and do that off to the side over here. The derivative with respect to x of x squared plus 1 square root. That's the same as the derivative with respect to x of x squared plus 1 to the 1/2. And now I can say, okay, take the 1/2, bring it down, subtract 1 from the power. So that's going to be 1/2 x squared plus 1 to the power negative 1/2. But now because of the chain rule, I have to multiply by the derivative of that, which is just going to give me 2x. I notice that my 2's divide away. 2 divides 2. And since that's got a negative power, I can bring it in as part of the denominator. So here, let me leave that x in the numerator, and let me write this in the denominator as square root of x squared plus 1. So that's the derivative of my denominator. It's going to be x over the square root of x squared plus 1. Okay, so, well, that's the reciprocal, right? If I take 1 and divide it by this, that's the same as multiplying by the reciprocal. So here, that's going to give me the limit as x approaches infinity. This radical comes to the top. And in the denominator, I'm left with just x. Okay, so that's, well, that's different, but it still doesn't really look any better. In fact, the only thing that happened was it flipped upside down. Okay, well, maybe I should use L'Hopital's rule again. Well, maybe, but it's going to turn out not to work out. Let's actually do that, right? Take the limit as x approaches infinity. If I take the derivative of the top and the derivative of the bottom, well, again, I know the derivative of the bottom is going to be 1. The derivative of the top, the derivative of the square root of x squared plus 1, we saw that's x over that square root. Now, of course, dividing by 1 doesn't change anything, so I can get rid of that 1 right there, and that's going to equal to the limit as x approaches infinity of x over the square root of x squared plus 1. And notice we're right back where we started. So that's indeterminate. L'Hopital's rule gets me something else that's indeterminate. But then using L'Hopital's rule again gets me something else that's indeterminate, and then I'm back where I started. If I did it again and again and again, I would just keep going back and forth between these two answers, and neither of them give me a result. I would keep going back and forth between these two limits, and none of them are going to tell me what the limit is. So here, can I use L'Hopital's rule? Yes, because it does satisfy the conditions required by the theorem. But for practical purposes, no, you don't want to use L'Hopital's rule here because you'll never actually get an answer. So how do we do this one? Well, we don't use L'Hopital's rule. To do this one, we're going to use something that we did all the way back in Cal 1. In fact, the end of Chapter 1 in Cal 1. Let's remind ourselves of how to take that kind of a limit. Here, we're going to multiply top and bottom by 1 over x. Okay? So multiply top and bottom by 1 over x, like this and like this. Here, multiplying top and bottom by 1 over x, that's x times 1 over x. That's just the number 1. But over here, well, I'm having a hard time dividing because the square root can't really be divided by that x. Oh, it can as long as I have these written with the square root also. So here what I'm going to do is I'm going to write this as the square root of x squared. That still means 1 over x. After all, x is positive, so it won't mess any of my signs. I won't accidentally have a negative when I shouldn't. But now, because they both have radicals, I can merge them together as a single radical. So I can write that as square root of x squared plus 1 over x squared. If you were to simplify all this out, you would get this again. If you're not convinced of that, pause the video and try it. That will give you that. But now this can be simplified dramatically. I can now write this as the limit as x approaches infinity of 1 over x squared is just the number 1 plus 1 over x squared. Notice that these are both constants. It doesn't matter what happens to x. I don't care if the limit at x, I don't care if I have a limit as x approaches 5, 100, 1,000, infinity, or negative infinity. These stay as they are. The only thing that's being affected is this term here. But as x approaches infinity, what happens to 1 over x squared? As the denominator gets bigger, the entire expression goes to 0. And so all that's left is 1 over the square root of 1 plus 0. Or in other words, it's 1 over 1. So keep in mind, L'Hopital's rule is a nice tool to use for indeterminate forms. It's not the only thing that's going to work, right? You can't just say, oh, I know L'Hopital's rule, that means I know how to find every limit in the world. There's plenty of them where it won't work. In fact, let's see another one. Let's say we want to find the limit as x approaches infinity of x over x plus the cosine of x. Notice that's also indeterminate. All right? Let's see here. As x approaches infinity, that's going to be infinite. That's going to be infinite. And if that's already infinite, plus, cosine is never more than 1 or less than negative 1. So if that's infinite over infinity plus 1, infinity minus 1, whatever. Plus or minus 1 does not change what happens as this approaches infinity. So this is still indeterminate. It's infinite over infinite, right? So let's say I try to use L'Hopital's rule on this. All right, well then by L'Hopital's rule, I'm too lazy to grab a red pen, so blue will have to do there. By L'Hopital's rule, I can say, okay, that's the limit. As x approaches infinity, the derivative of x is just 1. The derivative of x is also there, just 1, plus the derivative of the cosine of x is negative the sine of x. So let's just say plus a negative sine of x. Okay. Notice that this thing here is undefined. And you say, oh, so let me use L'Hopital's rule again. No, that's not what I mean. This is not indeterminate. It's undefined. Remember, the sine of x oscillates. It bounces back and forth between 1 and minus 1. These are both constants. So here, this is going to go back and forth between 1 over, well, let's see, 1 minus sine of x can range anywhere from 0 to 2. So this is going to bounce back and forth between 1/2 and, well, other numbers. And since the sine function is periodic, it's going to bounce back and forth between those numbers forever, back and forth and back and forth. However, if you didn't realize that, you would say, oh, okay, well, that's undefined. Let me use L'Hopital's rule again. Here, I really should have to grab the red pen now, right? Here, this is not correct. This is not valid. Because again, L'Hopital's rule only functions if you have something with the form 0 over 0 or infinity over infinity. This is neither of those. So, using L'Hopital's rule here would give me the limit as x approaches infinity. The derivative of 1 is equal to 0. The derivative of 1 is, again, is equal to 0. Plus, that's going to be the, oh, I guess it should be minus the cosine of x. And here 0 over anything is 0, right? So you might be tempted to say, okay, well then that must just be 0. But that's nonsense. Because here, this is not a valid expression. L'Hopital's rule can only be used in the case where your limit is of the form 0 over 0 or some version of infinity over infinity. So that is not the correct answer. You say, well, okay, but is that still right though, even though that's the wrong way to get it? No, that's not the right answer at all. To see how this one works, again, we're going back to a technique from Cal 1 called the squeeze theorem. Note that the cosine of x is bound between 1 and minus 1. So here we can say, okay, cosine of x. That's bound between minus 1 and 1. Okay, so if I add x to that, well, that's the same as adding x to this one and x to this one. Okay. Oh, but now if I reciprocate this, that reverses my inequalities. Okay, but it's still bounding it. And if I multiply everything by x, that gives me an x in the numerator, just like that. So x over x plus cosine of x is bound between these two expressions. So now let me take the limit as x approaches infinity of all of these. If I take the limit as x approaches infinity of x over x minus 1, that's going to bound the limit as x approaches infinity of x over x plus the cosine of x, which is going to be bound on the other side by the limit as x approaches infinity of x over x plus 1. And both of those limits are 1. Right? Either you divide everything by x like we would in Cal 1, or if you like, you actually can use L'Hopital's rule on this one. This is the form infinity over infinity, and if you take the derivative of the top and the bottom, you get the limit of 1 over 1, which is 1. And same thing over here. So if you want to use L'Hopital's rule on these, that would be acceptable. So here, by L'Hopital's rule, that's just equal to 1. And same thing over here. By L'Hopital's rule, that's just equal to 1. So here, these are both 1. This must be stuck somewhere in the middle. Oh, so that must also be 1. So the limit that we were looking for as x approaches infinity of x over x plus the cosine of x is equal to 1, not 0, the way we would have done if we didn't pay attention to the conditions of L'Hopital's rule. So be very mindful of that. Sometimes L'Hopital's rule will not work because, yes, it's a valid thing to use, but it doesn't actually ever give you the answer. Other times it won't work because it's just not valid to use. We don't meet the conditions. So be very careful with that. As our last examples here, let's take a look at just a couple of examples of some indeterminate form which is not 0 over 0 or infinity over infinity. Now you might say, well, then that just means we can't use L'Hopital's rule. Well, that's true, we can't. But even though we can't use L'Hopital's rule to that problem, if we can use some algebra to rewrite that problem, then maybe we will be able to use L'Hopital's rule to the new rewritten problem. So let's take a look at a couple of examples of that. So for our first example, let's go ahead and try the limit as x approaches 0 from the right of x to the third times the cotangent of x. So you'll note for this problem, we have, as you approach 0, well, clearly 0 to the third power is still 0. As you approach cotangent of 0, well, cotangent is undefined at 0. Oh yeah, but the reason for that is because there's an asymptote there. This goes off to infinity. So here, this looks of the form 0 times infinity, which again, that's indeterminate. Anything times 0 should be 0, but of course anything times infinity should be infinity. So here, it's like, the unstoppable force versus the immovable object. What happens when you pit 0 times infinity? What does that equal? So this is not of an indeterminate form that you can use L'Hopital's rule on, but we can rewrite that expression in other forms. For example, cotangent is the reciprocal of the tangent function, yes? So that means that we can rewrite that as, instead of times cotangent of x, we can say divided by tangent of x. Here I'm going to write that in, I'm going to write an extra step in between. It's not really necessary to do it this way, but I'm the professor, that means I have to show all the extra steps sometimes. Cotangent of x can be written as 1 over tangent of x. Notice, if this is going to infinity, its reciprocal is going to 0. Yeah? Again, as this approaches infinity, this is getting infinitely large, its reciprocal is approaching 1 over infinity. Or in other words, 1 over a very large number, that approaches 0. Okay, so we can rewrite that as this. These mean the same thing. But now I can write this as the limit as x approaches 0 from the right of x to the third over the tangent of x, like this. And notice now, the tangent of 0 would be 0, and 0 to the third would also be 0. So this, you can't use L'Hopital's rule on. Same thing with this. But once you rewrite it in this form, 0 over 0, that's perfectly valid now. So let's go ahead and give that a try now. If we, I'm out of focus. Let's see, there we go. It's a little better. If we now use L'Hopital's rule, we can now say that's equal to the limit as x approaches 0 from the right. That part doesn't change. The derivative of x to the third is 3x squared. The derivative of the tangent of x is secant squared of x. Okay. Now remember, we have to check to see if that's if that's indeterminate or not. If this is indeterminate, we can continue to use L'Hopital's rule, 0 over 0, infinity over infinity. However, if this gives you an answer, that's it, you're done. So be very careful with that. Don't just use it blindly. It depends on whether or not it meets the criterion for using L'Hopital's rule. So let's see here. If we have that x approach 0, let's see here. This would be 3 times 0 squared. That would be 0. Okay. Secant of 0, that's just 1. Secant of 0 is 1. Squared is still 1. That's not indeterminate anymore. That's 0 over 1. So always check. Every time you use L'Hopital's rule, you have to check to see, is that going to give me something valid, or is that still indeterminate? Okay, so that's not indeterminate anymore. We would not use L'Hopital's rule anymore. So here, that's just going to give me 0. So here, the limit as x approaches 0 from the right of x to the third cotangent of x, that's equal to 0. So in this particular case, 0 times infinity was equal to 0. Now be careful, that's not always true. In other indeterminate forms like this, you might have 0 times infinity is equal to infinity, 0 times infinity is equal to 5. There's no way of knowing ahead of time until you actually go through and compute. Generally, anytime you have something like this, 0 times infinity, 0 times negative infinity, that form of indeterminate form, what you're going to do is you're going to take one of these, reciprocate, and then multiply. I'll say that again. 0 times infinity, 0 times negative infinity, anything like that. Take one of them, reciprocate, and then multiply them together. That'll give you something you can use L'Hopital's rule on. Which one do you want to reciprocate? That's up to you. In this case, I went with this one because I didn't want to have a reciprocal function and a trig function. I'd rather stick with just polynomial and trig. But if I had flipped this one instead of this one, I would have gotten the exact same result. So just pick whichever one you feel like reciprocating. Let's take a look at another example. A little bit different from this one. It'll still be indeterminate, but not quite the same way. Let's say we're going to take the limit as x approaches 0 from the right. From the right of x to the power 1 over x. Notice, as x approaches 0, that's going to approach infinity. That's going to approach 0. So this is of the indeterminate form 0 to the infinity. Of course, 0 to any power should be 0. But anything to an infinite power should be infinite. So it's sort of like this. Which one's going to win out? So let's give this a try. In general, anytime you have something of the indeterminate form, something to a power, things like 0 to the infinity, 1 to the infinity, infinity to the 0, anything of that nature, you're going to use this technique. We're going to begin by pretending we already know the answer. We're going to say, okay, I took the limit as x approaches 0 of x to the power 1 over x, and it gave me an answer, and that answer was y. Okay? Now I'm going to pretend that I know the answer. Oh yeah, no, the answer is y. Okay, well, what's y? Oh, well, there it is. It's y. Yeah. Well, yeah, but what is y?
I heard. What's y?
Well, it's a number, and you just sort of pretend. Oh yeah, no, I got it. Okay, well, yeah, but can you tell me more about it? Oh, sure, I can tell you that it's a number, and so I can do things to it like I normally would to any number. Oh, like what? Well, I can take its natural logarithm. Okay, why would you want to do that? Well, natural logarithm of x to a power. Hey, going back to a previous section, we saw that one property of logarithms is I can take this number and just pull it out. So I can write this as the natural log of y is equal to the limit as x approaches 0 from the right of 1 over x times the natural log of x. I could just merge these together as one fraction. So let me write that as the natural log of y is equal to the limit as x approaches 0 from the right of the natural log of x over x, like that. So now let's check to see if we can use L'Hopital's rule on this. As x approaches 0, obviously that's just 0. As x approaches 0, that's, that's actually not 0, is it? That's going toward negative infinity. Remember what the graph of the natural log looks like. As you approach 0 from the right, your graph goes toward negative infinity. So here, this is not indeterminate in the form that you can use L'Hopital's rule in. That's going to be going toward negative infinity, and that's going toward 0. In fact, we may be better off looking at the form right above it. Here, these mean the same thing, but as x approaches 0, again, that's going toward negative infinity. As x approaches 0, that one's going toward infinity. So two things that are infinitely big, that's going to give you something infinitely big. This goes off to infinity. Negative infinity, since it's going, so that's toward negative infinity. That's toward infinity. Positive times negative is negative. Yeah? So here, this is going toward negative infinity. So here, this line is not wrong, but it's just not necessary. We could have stopped one earlier. All right. So here, note we didn't even use L'Hopital's rule. If this had been indeterminate, we would have, but it turns out we don't even need it for this problem. This approaches negative infinity. Okay, so the natural log of y approaches negative infinity. Oh, well, remember, here's the natural log. That's the graph. So the natural log is approaching negative infinity. Oh, well, it approaches negative infinity as you go to 0. Oh, okay. So then that means that this whole thing is going to 0. So the natural log of y is going toward negative infinity, so y is going towards 0. You can see that from the graph. As your natural log goes down toward infinity, it's because your argument was headed back toward the origins, headed back toward the asymptote here. Okay, but y is equal to that limit you were looking for. Thus, the limit that we want as x approaches 0 from the right of x to the power 1 over x is equal to 0. And that's our limit. Note that anytime you have an indeterminate form that involves a power, you're going to take the natural logarithm of both sides, you're going to manipulate this side, and then evaluate the limit over here. Don't forget that in the end, you have to evaluate it to get rid of the logarithm to end up with just y, just as we do here. All right, we have natural log of y is equal to this, but again, we want to find just what y is equal to. On the other hand, in the event where you have an indeterminate form where multiplication is involved, 0 times infinity, something like that, 0 times negative infinity, you're going to reciprocate one of them and then rewrite and use L'Hopital's rule.